Greetings to one and all. We once again meet on another session of ePathshala. Welcome to ePathshala Architecture Project lecture series for MArch students. This is the second part of elevators and escalators for the paper Services in High-Rise Buildings. For a quick glance of what happened in the previous session, here are the takeaways for you. Introduction to tall building and its definition, factors and design criteria for elevators, common mistakes in design considerations, calculation versus simulation based design, optimizing traffic performance. Here's a small video on how elevator works, courtesy Discovery Channel.
No city skyline would reach these heights if it weren't for this machine. Before the elevator, buildings rarely grew over 5 stories. They perform billions of rides every day around the world. Among the safest ways to travel, there's less than 1 chance in 12 million that something will go wrong with the elevator you're riding in. Let's see how they work. The most popular elevator design is the roped elevator, where a car is raised and lowered by steel cables. The machine's muscle lives up here at the top of the elevator shaft. Its ropes attached to the car and loop around a sheave, a pulley with grooves to grip the ropes that's connected to an electric motor. Turn the motor one way, the elevator car goes up. When the motor turns the other way, it goes down. A counterweight lives on the other end of the ropes to offset the weight of the car. It's usually about half the weight of a fully loaded passenger elevator. So, on an average ride, the two are perfectly balanced. All the motor needs to do to move the car is provide a nudge to tip the balance one way or the other. This system saves energy as well as wear and tear on moving parts. Once the car is moving, the motor's only job is to control one of the 2 falling objects. Both the car and counterweight are attached to guide rails inside the shaft. They keep everything from swaying back and forth and also give a backup set of brakes something to grab onto. If anything goes wrong with the motor, hydraulic fluid is cut off, and that automatically releases this brake that seizes the ropes for a quick stop. Technically, one of these steel ropes is enough to hold up both the car and the counterweight. The rest are there for backup, in case one snaps. But what if the whole set is cut? Don't worry, it still won't plummet. This machine has a built-in failsafe. There's a governor located beside the motor, with its own pulley and separate cable attached to the car. There are 2 spring-loaded metal hooks called flyweights inside the governor. If a car free falls and the governor spins too fast, centrifugal force pushes the hooks out. They seize ratchets on the fixed inner rim and stop the pulley. The governor's rope jerks on an arm on top of the car, and this locks the brakes. The idea of the rope elevator is simple enough. One side goes up, the other goes down. It just took a couple of thousand years to figure out how to stop it. It's easy enough to drive, but without brakes, we'd rather walk.
Let us look at the technology and comfort. High-speed elevator technology. It is natural that pricing increases almost exponentially in proportion to the height of the building, because With the increasing height, the constraints and challenges also increase. The same applies to cable weight and energy consumption. As we go against the gravity, the energy consumption also increases. Reciprocating air displacement in elevator shaft, it is a very important constraint. One important challenge is overcoming noise problems, which arise because of air resistance, whining and whistling noises inside the car, aerodynamically designed exteriors prevent hammering sounds. Soundproof to reduce noise emission levels within the car has to be done. Noise transmission through car ventilation system also occurs, which has to be taken care. A plunger effect is generated because of the movement of car in the shaft. It is caused by the car's movement inside the shaft. Shaft partitioning walls are there, and there are perforations and or interconnecting openings as the cars bypass between the floors at the headrooms and at the base of adjacent spaces and so on. So that needs to be overcome. Coming to car guidance system, it is very, very important on how do we go about designing the car system. Talking about the alignment of tracks, it is very important to reduce vibrations or movements. And since it is going to, the cars are going to move up and down for a length of time, durability of tracks are very, very vital, and therefore we make use of heavy duty usage tracks for the high rise elevator system. Guidance surfaces and welds, they have to be totally flushed so that they don't hit any components that are around the shaft. Mounting points, positioning within micron, and there has to be very, very precise execution of work. High quality roller guidance system have to be in position. They have to withstand the effect of building settling. As we are all aware, any building over the period has the tendency to settle depending on the soil condition, and as the years pass, as decades pass, there are issues of settlement, and these elevator systems have to take care of that challenge. Response of the building's structure to thermal and climatic changes is very, very important, and it is very difficult to predict the behavior of thermal and climatic changes in response to, and therefore the elevator system has to take care sufficiently to be durable and lasting for these kind of challenges. Pressure difference challenge. We all are aware that the pressure varies as we go above. Between the base and the top of a building's elevator shaft, there is a difference in pressure, and this cannot be overlooked, and this needs to be taken into account. Elevator shaft doors therefore have to be in such a way that they are airtight by various methods. For example, by implementing interlocking labyrinth seals. This is a way of taking care of elevator shafts airtightness. The main entrance level, we are aware that there is a direct passage to the outside air, and this should be eliminated by double airlocks. Elevator machine rooms at the top also have to be airtight, otherwise we may experience a huge problem because of pressure difference. Ride has to be comfortable for the occupant who are using the cars, and therefore we have to ensure a certain factors into account. For example, we have to see the noise levels in the interiors, and we have to take into account the traverse car vibration. We need to ensure that the noise levels are 48 to 52 decibels for superior ride comfort. Traverse car vibration have to be minimized to the maximum extent. High demand on suspension, track and roller guidance system help to a great deal in taking care of the vibration. We are aware that as the high rise structures or the tall buildings increase in the number of floors, the constraint on the speed of the car is also very important, and there is a limit to which only we can have speed. So, there are conventional elevators and there are express elevators, and we make use of these combination. High speed or greater than 3 meters per second, we make use of additional technological and alignment measures for overcoming the challenges with respect to high speed elevators. Axial acceleration and deceleration are very important, and it needs to be very smooth in terms of picking up of speed and in terms of the braking system to bring down the speed. When the elevator car stops at a particular floor, the jerk factor also has to be taken into account, and we need to bring in an almost smooth landing experience for the occupant user within the car. Pressurization and depressurization. At descent speed above 8 to 10 meter per second, car pressurization can be painful to passengers' ears. To take a similar comparison, when the flight is taking off or landing, a person may feel pain in the ear, and that is exactly because of the pressure difference. Depressurization on ascent less painful than pressurization on descent. This needs to be understood in principle and put into practice when we are executing the project. Talking about car occupancy, it should be limited to a maximum of 70% of the theoretical load limit. Even though the numbers may say a certain maximum capacity, it is always preferred to keep the count lesser for the long life and the good workability of the elevator system. There are possibilities that there may be eventualities which require people to evacuate the building, and there may be people in the elevator system, and when we are evacuating from the elevators, it has to be done in a phased manner, and one of the ways to do is the people disperse into the service area and come out through the safe zone. There are possibilities of using twin lifts. Operation of two separate elevator cars within one shaft. This helps a great deal. Use the same track and elevator shaft access points, but have separate cars, separate drives, suspensions and control system. Triple layer mechanical and electronic safety systems are employed. The upper car serves destination in the top half and lower car the bottom half. This is one way of dealing with it. So, what happens is additional capacity of approximately 30 to 40% per elevator shaft is achieved. Large elevator groups, and we require fewer shafts, and this is the advantage of making use of this kind of a concept. Many high-rise building, keeping into account space constraint and cost constraint, make use of this methodology of planning and technology. So, as we have seen additional optimizing possibilities, we have double deck elevators and twin elevators. Indicative images are shown here. So, here is a double deck elevator. We can notice that one deck is above the other and is a realistic image. This is used in scenario wherein alternative floors are used for landing. Say for example, this floor, this particular elevator is used for all the odd numbered floors, and this particular car is used for all the even number of floors. So, typically an end user who wants to go to all the even floors, say for example floor number 10, the person needs to come to the second level and then from there go directly to floor 10, whereas in this case the person who wants to go to floor number 9, they just need to come here and they can go to the odd floor number 9. This is the concept of twin elevator, wherein the same shaft is used for accessing various floors, and this is a image showing the core is there and twin elevators are used here. This is an exposed kind of an elevator. Twin lifts are ideal for various situations. For example, high-rise building with high peak demand. During the morning hours, if the building is predominantly office occupied, then morning there is a peak demand and there are a lot of rush during the peak time. In such case, twin lifts are very useful. Building with large elevator groups, that is also in principle very useful. Building with a lot of between floor traffic flow, this is also possible, and therefore you have three different scenarios in which twin lifts are ideal for situations. Twin lifts can only be implemented under the following conditions: the destination control, at least one conventional elevator must be there, holding a pit of at least 8 to 10 meters deep. Let us take a look at this image here. This is a typical image of a traditional elevator group where independent elevator shafts are there and elevators reach out to each floor, whereas in this case you can see that there is a twin elevator, lower and upper, whereas there is an independent elevator core that goes to all the floors, and we are saving one shaft here. So, it is a big saving in terms of space. As far as cost saving is concerned, it needs to be worked out to rightly identify the exact cost mechanism. Here is an example of Type A 101 elevator technology. Type A 101 measuring 509 meters, I am sorry. The office block has 50 elevators, 34 double deck elevators and 2 fast elevators. The total investment in elevator technology is approximately $85 million. The 2 shuttle elevators for the public access to the observation deck on the 89th floor. The ascent speed is 16.8 meters per second or nearly 60 kilometers per hour, whereas the descent speed is 10 meters per second or 37 kilometers per hour. You may clearly notice that the ascent speed is more than the descent speed. The elevator cars are airtight pressure cabin and equipped with pressure regulation system. We just now understood how pressure adjusting mechanisms are very important. Pressurization on descent is done for the comfort of the occupant. Elevator cars are fitted with upper and lower capsule shaped spoilers. Here is a sample video of what is the experience inside an express elevator. This is an amateur footage from YouTube by the user using the elevator in Type A 101. We can notice that the occupants are boarding the capsule from the lobby, and on the display is the overall profile, section profile of the building, and it indicates various aspects: the height of the building, the speed at which it is traveling, and there are aesthetic detailing done to the ceiling also. And here it shows how fast the car is ascending to the higher floors, and slowly you can notice that at a very fast time people are reaching the destination, the deck. They are almost reached, and you might have noticed how the speed came down, and now once it is open, they reach out to the sky lobby. So, the various challenges that are faced are such as vibration within the car. It is eliminated by implementing a triaxial active control roller guidance system. Active mass damping fitted to each elevator to minimize lateral movement. So, there are lateral movement as well as axial movement which needs to be taken care. There is equally important necessity about the braking system. In case of an eventuality, brake pads are made of silicon nitride ceramic compound for safety braking system. The office block floor 9 through 84 is accessed as though it were made up of 3 individual building segments. Transportation to and from the sky lobbies on the 35th and 59th floor is provided by 10 high speed double deck elevators. Each of the 3 sub segments is fitted with its own local double deck elevators, and the use of double deck elevators doubles the transportation capacity per shaft, and it clearly indicates the high usage of the elevator system across the floors. The 2 cars are suspended independently of one another in a frame. Type A 101 also houses 4 exclusive passenger elevators to Sky Restaurant and Executive Club, 4 general purpose goods and firefighting elevators, 6 car park elevators, 11 passenger elevators at the base for commercial purpose, and 50 escalators. And Type A 101 is a classic example of a combination of various types of elevators and escalators. In summary, we see that meticulous and impartial capacity analysis and detailed simulation are necessary for designing any elevator system. Simulation also does not come easy. We might imagine that though simulation is happening through a software, it is easy, and as we just feed the input, we readily get the output. It is not so. The assumptions that we make during simulation are very critical and vital, and based on the right assumptions we get the simulation results very accurately. If the planning and the simulation factors are independent, the results that we get may have implications on cost and wastage of materials and time at site. Therefore, meticulous preparations are needed and planning are needed before getting into detailed simulation. Elevator configuration and physical and or dynamic zoning is very important in terms of planning. Correct choice of group control system is also vital. The right choices have to be made first time round. As far as possible, most of the assumptions have to be made appropriately in the very first time, and as we iterate, we need to make sure that we are evolving in the design process exercise and not redoing the design exercise. Safety and comfort within the car at high speeds are very important. Safety is as important as comfort. Safety in terms of braking system or the pressurization system, comfort in terms of keeping the air quality, the temperature control, and various other factors are also there. Sometimes an ambient sound system is also provided, a lighting system, as you saw in the video shown, the right kind of ambience is maintained for the end user so that they do not realize the actual high speed that they are traveling. Group control system is also very important, because depending on the kind of grouping, it reflects on the building's occupancy system, and therefore group control system plays a vital role in day-to-day usage of the cars. High-rise elevator systems costs are to be taken into account because the buildings the promoter who are executing the project, the elevator costs are one of the major chunk of costs that come into picture, and the striking the right balance between planning, technology, cost cutting have to come into picture. Long term benefits have to take into account, and there are sustainable methods of generating energy through elevator systems. These can also be considered while planning for high rise elevators. This is a typical image of a CCTV building in Beijing. This is the view of the building. You can see how much cantilever on both sides happened, and this is a typical drawing of it, and you can see the overall lift shaft, elevator shaft, and a quick glance into the building's zones. There is a public lobby here, there is a tower lobby, and there are express elevators, executive elevators here, and VIP elevators. There is a sky lobby here, and there is a tower lobby here. And this building is a clear example of how unique each tall building can be and how challenging it is to design elevator systems to each building on a one-on-one basis. So, with this we conclude the part 2 of this series on elevators and escalators for high rise buildings. Thank you.